Okay, hello everyone, and thank you very much for joining us today. And thank you for the School of the CECS for providing us such a wonderful platform to promote and popularize our research and teaching. My name is Mingjie Lin, and I want to say a little bit about me. And I joined UCF in 2011, and I'm currently an associate professor in the ECE department. I got my Ph.D. from Stanford and at 2008, and then worked a couple of years as a senior engineer at Tabula, which is a FPGA startup company. And so most of my career basically try to study and investigate the FPGA-based reconfigurable computing and its application in various areas, for example, secure computing, AI, and robotic control. So I also served in various venues and as reviewers and program chairs, so on and so forth. So let's talk about my research and teaching focus. And as I said, my research and teaching mostly focus on the FPGAs. FPGA technology. FPGA stands for Field Program Gate Array. And so this is a billion-dollar industry, and I believe is also the future of the digital circuit design. The FPGA technology itself is very sophisticated, and it contains both the hardware part and the software part, and which I will discuss a little bit and relate to my research. And most people probably don't know, and the FPGA itself is not just a single device. Instead, it's a very sophisticated computing system, like what I showed here. And you can see it's a very sophisticated, almost like a motherboard. And you have an FPGA device with all kinds of I/O modules, and they interact with each other, and it can be used as a very powerful computing engine and do a lot of real-time computing and secure computing stuff. And FPGA itself is very complicated, and I think one fact probably most people didn't know is that they see FPGA as a hardware, a piece of hardware. But in reality, FPGA technology, the most interesting part of the FPGA technology actually is the software, which is the software algorithm behind this technology, and which is part of my research. And also teaching is also centered around at FPGA technology. I have a 3-class sequence and teaching students from scratch until they become very good at using FPGA board to design real application. So my bottom line is FPGA technology is amazing computing technology, and also is a very effective research platform. So here's my research landscape. And my research actually consists of 3 directions or 3 modules. The first part is related to the fundamental FPGA technology, relates to circuit design, how to design and implement a very effective FPGA fabric, and also studying the fundamental algorithms behind the FPGA technology. For example, the memory optimization, placement, logic synthesis, and also the routing. And the second track of my research is mostly about how to use FPGA device to ensure security in computing. This is like a more recent direction my research group is pursuing right now. And it relates to secure non-volatile memory and secure storage, and sometimes we do encryption, decryption. Finally, the third research direction, and it's about the more like AI or robotic control type of computing applications. And over the last couple of years, our research group have been developing various robotic platforms to research on the FPGA-based computing algorithms. We mostly focus on distributed control, sensor fusion, and also some kind of novel reinforced learning algorithms. And we know that in this school, we have many wonderful AI researchers. And but our research mostly is taking the AI research from the hardware perspective instead of just focus on algorithm or theoretical studies. So here's I picked 3 ongoing projects to highlight my research. And the first one, this project is a joint work with Dr. Awad, and is sponsored by DARPA SPA, and it's a 3-year and very large project, and involves like 6 students, probably together it's kind of 10 students. And our motivation is the NVM, the non-volatile memory technology, is going to take over the majority of the computing industry because it's so powerful, so parallel, so high bandwidth. However, the nature of this kind of storage can cause a lot of security concerns because information can be retained after even power down. And this creates all kinds of unique security related problems. Without getting into too many details, and our challenge mostly is about how to design an efficient computing system and using FPGA fabric and to ensure security and the robustness of a computing platform. And our approach basically involves two sides. The first one is about how to develop novel schemes for encryption and data integrity verification. We mostly use very sophisticated software-based algorithms, such as Merkle tree cache, these kind of algorithms. The second part of this research is about how to develop novel scheme and for integrity verification metadata. So the idea is that a lot of current secure computing system, once the power is down, you potentially can lose the security related metadata. That means even your data is protected, however, you cannot safely cover from your current data storage state. And this causes a lot of problems. That's the major reason why DARPA wants to develop a new kind of computing system. And so our research outcome will be, we'll develop FPGA-based computing system, and with a lot of hardware controller and NVM controller, memory controller, all these controllers will be developed by us from scratch with some unique hardware features. So it's a lot of work and also quite involved. So the second project is robotic control. And so this is sponsored by Air Force Research Lab. And the idea behind this project is that a lot of times for most robotic systems, and you have very dynamic environment, meaning you have dynamically changing obstacles. And in this particular project, we kind of set up this, we have a dual robotic arm, and one arm is working and pretending there's nothing else in the environment. The other one actually need to dynamically learn how to adapt this moving, the other moving robotic arm. So basically this is dynamic changing obstacles. And we kind of develop new algorithms, and also we develop a new kind of hardware implementation to ensure this kind of learning can be really fast, can be very robust, and involves a lot of FPGA-based research. And our current state of outcome is we have a system about 25 times faster in learning performance compared with the state-of-art implementation. So the third project is sponsored by NSF, and it's more related to the fundamental research behind the FPGA technology, and it's mostly related to the software algorithms behind the FPGA placement and routing. Especially, we focus on this particular branch of FPGA technology, which is called high-level synthesis. The idea behind the high-level synthesis is this, and we know right now if you use HDL, hardware description language, such as Verilog or VHDL, to develop and implement hardware, it's very tedious, very easy to make a mistake, and a lot of people don't have much experience. The idea behind this high-level synthesis technology is this allows the user to write a C-like program, then use a hardware or use a software package compiler to automatically compile it into hardware. Basically, that's the idea. So all the software engineers can become very good hardware engineers in FPGA technology. And this involves a lot of memory optimization. One thing unique about the FPGA technology is that FPGA has a huge amount of aggregate memory bandwidth. However, to maximize the peak memory bandwidth is really hard because it has a lot to do with the special memory access pattern, depending on your specific applications. So this research is really about how to use mathematics-based framework to optimize this memory allocation and automatically generate very efficient memory code to allow the high-level synthesis to synthesize very high-performance FPGA design for any kind of general purpose application. So this can find a lot of applications in AI, in robotic control. And another application for this kind of research is it can also be used with the emergent memory technology, such as HMC. HMC is kind of like a 3D type of a memory technology, has multiple layers. You also can read different planes in parallel. This is really high bandwidth and a really high-tech type of memory. And so this research is also can be used in that regard. So let me just spend a couple minutes talk about my future research plans. And my near-term plan is very simple, and just finish up my current ongoing research projects I just described. And also I will focus a lot on the FPGA-based education, because what we find at the UCF is that there's, because of our nearby space industry, because of nearby military base, we have heard there's a huge demand for FPGA programmers, for FPGA developers. I hear this kind of requests, hiring requests from Harris, from Lockheed Martin. In fact, several of my past students, they are already working for these companies. It turns out there's a huge demand for FPGA-based engineers. So I really wanted to make sure the UCF becomes one of the educational basis for this FPGA technology. My long-term plan is I want to focus my research in pretty much these three directions. One is about secure computing. This involves how to protect computation, how to allow computing, cloud computing, to be more secure, and how to prevent hacking to the hardware. So it's these kind of directions, how to prevent the hardware-based virus to infect computing platforms. The second direction will be the emerging computing paradigms, and this mostly about the memorist-based computing engine. Finally, AI-based autonomous computing. Because of these directions, I'm really looking forward to collaborating with computer scientists from the CS department, material scientists from Nano Center, from the other centers, and also even biologists, because I'm really interested in this kind of emerging computing using the biology. It's kind of bio-inspired computing is also one of my research interests. Finally, I want to spend 1 minute to acknowledge, and we cannot live without these funding agencies. And over the years, there are so many wonderful agencies have supported our research. And I have many collaborators, and all of them have helped us tremendously. Finally, my current graduate students, and they are really the main reason for all the research outcomes we have today. Thank you very much. That's the end.